Hello, this is lecture number 1 for Math 609. We will start the material with the following. We will discuss at first how to solve algebraic linear systems of equations, AX is equal to B, where X is an unknown vector, A is the matrix of coefficients associated to this system, and B is the right-hand side. We start with this problem because, as we will see further, we will have different problems whose solution will end up with the need to solve a linear system of equations. And in general, a lot of problems from real life are problems that in order to solve these problems, we end up solving certain algebraic linear system. And so algebraic linear systems are fundamental problems in many scientific and engineering applications. In general, when we have a problem at hand, we need to answer several questions about this problem. The first question is, does our problem have a solution? So in our particular case, we need to answer the question whether the linear system that we would like to develop numerical methods for have a solution. If the linear system has a solution, is it unique, or we have a family of solutions, and therefore maybe we need to characterize this family. In the case that the linear system has a unique solution, we have to answer the question, how can we solve this system via a computer in case the dimension of the unknown vector is very large? Because what happens in applications is that the problem that one needs to solve culminates into the need to solve a linear system for a very large unknown vector, for an unknown vector that is in a very high dimension. The next question is, what are the available algorithms for solving linear systems? How do we implement those algorithms? How do we choose a particular algorithm for our problem at hand? How expensive is a particular algorithm in terms of how many floating point operations do we need to do in order to solve a problem of dimension n, that is that means for an unknown vector that has n coordinates. How stable is our method? So if we make a little error in the data that we have, or if the right hand side, which will be given to us, is inaccurate, how does this error propagate when we try to solve the system? Or even if we have a method that is exact in the sense that it theoretically will give you the exact solution, when we try to implement this method on a computer and design or write a program for it, when the computer does the corresponding arithmetic operations, there will be inevitably a round-off error, and this round-off error will propagate through the computation. And then the question is the method that we're using going to be stable, and whether the method will propagate that error, and whether we will actually end up with a solution to our problem that is close to the solution that we're after, or we will end up with something that would not make sense. Also, sometimes the matrices that we have, the matrix that is associated to the linear system, has a special structure, And certain numerical methods are faster or are designed for matrices with a specific structure, and we need to know this method. We need to make use of the special structure of the matrix A, and therefore design a method that would utilize that structure and will perform better because of this inherited structure of the matrix A. But before going into details, I will just talk about the notation and certain facts that we need to know from linear algebra in order to continue further. We will discuss vectors X, which are column vectors, and are written in this form with n coordinates. Those coordinates can be either real numbers, and then we will denote that by writing X belongs to Rn, or these vectors are with complex coordinates, and we will denote this by writing X belongs to Cn. Sometimes we will write the vector as a vector row, and then we'll write T, which means the transpose of that vector. The matrices that we're going to deal with will be mainly matrices with real entries. And here A is written as a matrix of dimension m times n, which means m rows and n columns. The matrix can have also complex entries, and we will then denote this as writing A belongs to C m cross n. But in our algorithms, we will mainly deal with square matrices in which the number of the rows is equal to the number of columns. And as you all know from linear algebra, this is how a matrix is written. This is a matrix with m rows and n columns, where the generic element is aij, where the index I shows us the number of row where this element resides, and j tells us the number of column where this element resides. Examples of simple matrices that we're going to use. First, with I, we will denote the identity matrix, which is a square matrix. In our consideration, this will be a matrix of dimension m times m. This is a matrix where we have ones on the main diagonal and zeros everywhere else. We will discuss also upper triangular matrices. We will denote them by U, and those are matrices for which all the entries of these matrices below the main diagonal are 0, but the entries above the main diagonal or on the main diagonal may or may not be 0. Similarly, lower triangular matrices will be matrices for which everything above the main diagonal will be 0. And the elements on the main diagonal and below the main diagonal, which here they are denoted by Lij, with the obvious restrictions for the indices I and j, they may or may not be equal to 0. We will then continue with some definitions. A square matrix is called symmetric matrix if it has real entries, and it is such that the transpose matrix of this matrix coincides with the matrix itself, or basically this is a matrix for which the element Aij is equal to the element Aji. A matrix is called the Hermitian matrix if it has complex entries, if it is a square matrix and it conjugate transpose coincides with the matrix A. So by A star, we denote the conjugate transpose of the matrix. This is a matrix whose components are AJI complex conjugation. What is complex conjugation? So if I have complex number A plus IB, and I would like to look at its complex conjugate, which I denote by bar on the top. This is the complex number A minus IB. So what is changed? Just this sign here from plus goes into minus. And a matrix that satisfies this condition is called a Hermitian matrix. And if we have a Hermitian matrix, if we put here in this general equation, if we consider the case when I is equal to J, then we will have that AII is equal to AII bar, which means that on the main diagonal, the entries on the main diagonal coincide with their complex conjugates. And this is possible only if the entries are real. So if we have a Hermitian matrix, on the main diagonal, we have real numbers, and of the main diagonal, this element corresponds to this element. And the only difference is that in front of the imaginary part here we have plus, and here we have minus, and the same thing here. This element corresponds to this element, and the only difference between those will be that in front of the imaginary part you have in one place minus, and at the other place plus. Similarly, a matrix that is square matrix and has complex entries is called a skew Hermitian if the complex conjugate of the conjugate transpose of this matrix coincides with the negative of the matrix. Then I will remind you what is how we define a product between two matrices, A and C. In this particular case, if the matrix A is of dimension L times M, and the matrix C is of dimension M times N, so the number of the columns of the matrix A has to coincide with has to be equal to the number of rows of the matrix C. Then we can talk about the product of these two matrices, and the corresponding ijth term of the product matrix B, which is Bij, is given by this sum. In fact, what do? We take the ith row of the matrix A, and we multiply it scalarly by the jth column of the matrix C. So if we have, for example, here 3 components, here we have to have 3 components, then we multiply this number by this number, and to the product we add this number by this number, and to the product we add this number by this number. Another useful way to view matrix multiplication is the following. If we look at the matrix B and we denote by B1, B2, and so on, the matrix will be of dimension L times N, so Bn, if those are the columns of the matrix B. Then the jth column of the matrix B, which is the product of the matrices A and C, is basically a linear combination of all the columns of the matrix A, where the numbers in this linear combination are the components of the jth column of the matrix C. So if this is the matrix C, this is the jth column of the matrix C, and those are the components of the jth column of the matrix C. Those numbers here are used as linear combination in front of the columns of the matrix A. So here is the matrix A, and it has columns A1, A2, and so on, AM. And this is the jth column of the matrix C. So this number multiplied by this column, this number multiplied by this column, and so on, this number multiplied by this column will give us the jth column of the matrix B. What is the range of a matrix? The range of a matrix is the set of all y such that y is equal to ax for some vector x in Rn, provided that we consider a matrix with real entries. So what does that mean? When the vector x marches within Rn, then we look at the image ax, and then the set of all these vectors is called a range of A. And because of this description of multiplication of a matrix by a vector that I described, we can think of the range of A, which is a useful way to view it. It is basically the range of A is the space that is spanned by the columns of the matrix A. So if I have the matrix A and I look at its columns A1, A2, and so on, A, in this particular case, the number of the columns will be N. And then AX then would mean what? AX will be the matrix A multiplied by the vector X will be X1 A1 plus X2 A2, where X's here are numbers and A's are the vectors and so on, plus X n times AN, where ANs are vectors in the dimension Rm. And so the range of a matrix can be viewed as the space spanned by the columns of the matrix. A column rank of the matrix is the dimension of the space spanned by the columns of A, and rank of A, it is the dimension of the range of A, which is the same as saying that this is the dimension of the linear space spanned by the columns of the matrix A. A matrix of dimension m times n is is said to be a full rank if it has the maximum possible rank, and the maximum possible rank is the minimum between the number of rows and the number of columns. The null space of A is the set of all vectors that the matrix A sends to 0. So these are the set of all x's in Rn such that A times x is equal to 0. The transpose matrix of the matrix A is the matrix, we already used the symbol transpose to when we define the symmetric matrix. This is a matrix. So if the original matrix was of dimension m times n, A transpose will be a matrix of dimension n times m, and this is a matrix for which the columns of the matrix A become rows of that matrix. And if you have the product of A B transpose, then this is the B transpose times A transpose, which is the main equation that relates to the property to transpose a matrix. And the conjugate transpose, if A is a matrix of dimension m times n with complex numbers, complex entries, then A star is also a matrix with complex entries, but now it will have n rows and m columns. And the elements of this matrix, the ijth element of the matrix A star is equal to the jith element of the matrix I at the matrix I complex conjugate. And again, the same rule as for the operation here, that AB star is equal to B star times A star. As I mentioned in this class, we will be interested predominantly in square matrices, whether of dimension n or square matrices of dimension m, where their entries will be mainly real numbers. A matrix is called invertible matrix if there is a matrix which we denote by A inverse, such that A times A inverse is equal to A inverse times A is equal to the identity. And this matrix is called the inverse of the matrix A. And the basic property of taking an inverses of a product. So if we have two matrices of the same dimension n, and we multiply them, the inverse is this product, the product of the matrix A inverse times the matrix B inverse. Let me remind you that matrix multiplication is not commutative, so one has to be careful about the order in which one writes the matrices when they are multiplied by each other. For every square matrix, to every square matrix, we associate several numbers. One of the numbers that we associate to a square matrix is called the determinant of this square matrix. And there are various ways in which one can compute a determinant of a square matrix. In general, the formulas involve quite a lot of computations, and among the formulas that are known for determinant, I had chosen to write down this one, which is called the Laplace expansion along the ith row. And this is a recursive formula that computes the determinant of an n times n matrix via n determinants of n minus 1 times n minus 1 matrices. Easy way to compute determinant is only can be done only for matrices of dimension 2 by 2 and 3 by 3. So in case when you have a 2 by 2 matrix, a determinant of a 2 by 2 matrix is the product of the elements on the main diagonal minus the product of the elements of the main diagonal. And also there is a sort of neat rule to compute the determinants of a 3 by 3 matrices. But if you go to dimension higher than that, then this is quite a computationally intense procedure. However, if one knows the eigenvalues of a matrix, then the determinant of this matrix can be computed easily by just multiplying the eigenvalues of the matrix. Or if the matrix has a special structure, then determinants are easily computed. The determinant of the identity matrix is 1. The determinant of the lower triangular matrix, and here should be U. And the upper triangular matrix that we just defined are easily computed because they're just the product of the elements on the main diagonal. So if we have a lower triangular matrix, the determinant of this matrix is the product of these elements on the main diagonal. And if you have an upper triangular matrix, the determinant of an upper triangular matrix is just the product of the elements on the main diagonal. Another set of numbers that we associate with a matrix are the so-called eigenvalues of a matrix. If we have a square matrix of dimension n times n, then we associate with it n complex numbers, and where n is the dimension of the matrix, and these are the eigenvalues of this matrix. An eigenvalue of a square matrix is a complex number. And it is, we say that lambda is an eigenvalue of the matrix A with corresponding eigenvector V, which is non-zero. If when we apply the matrix A to the vector Z, we end up with multiple of the vector V, and this multiple is exactly lambda times V. So this relation here can be written, which I wrote further, can be written in the following way. We move this term on the left, and then we have AV minus lambda, and here we insert identity matrix times V is equal to 0. Anything multiplied by the identity is the same thing, so whether we write down the identity matrix or no or not doesn't matter, but it is then easier to pull out V to the right, and then we will have A minus lambda I. This matrix applied to the vector V is equal to 0. And since an important fact in the definition is that the vector V is a non-zero vector, and therefore we end up with the fact that we have a system of n equations with n unknowns, in this particular case, the vector V, that has a 0 right-hand side, but has a non-zero solution. And according to theorems from linear algebra, this is possible only when the determinant of the matrix associated with this system is 0, and therefore we have that the determinant of A minus lambda I should be equal to 0. Now, if one looks at the particular form of this matrix, this is the matrix A11, A12, A1n. Those are the entries of the original matrix A, A22, A2n, and so on. We have AN1, AN2, and then ANn. And from this matrix, we subtract lambda times the identity matrix, which is the matrix that has lambdas on the main diagonal and zeros everywhere. When we subtract two matrices, we subtract all the entries of the matrices, and therefore the matrix A minus lambda I will be this matrix, and we want the determinant of this matrix to be equal to 0. However, if we use the rules, even for example, this rule that I wrote here, the Laplace expansion, to compute this determinant, one finds out that this, in fact, if you write it down, you will end up with a polynomial of degree n, which is called a characteristic polynomial, corresponding to the matrix A with respect to lambda. And therefore, this equation here, called also the characteristic equation, will be an equation that is looking for the roots of a polynomial of degree n. And according to main theorem of algebra, every polynomial of degree n has exactly n roots, which are in general complex numbers. For example, we can illustrate that if we have the polynomial lambda minus 1 squared is equal to 0, which is a quadratic function, and it has two roots, 1 and 1, with so it has the root 1 with multiplicity 2, or we can have lambda minus 1 times lambda minus 2, for example, is equal to 0. This will have the two roots 1 and 2, or we can have something that if you have a quadratic polynomial, then the roots will be complex conjugate numbers, always a root that will be a plus ib, a plus ib, and a minus ib. So this is another list of all possible possible roots in the case when n is equal to 2. But in general, you can have n roots, and some of them may have higher multiplicities and some of them may not. But if you write them as many times as their multiplicities and write them down, each of them, then you will end up with a list of n numbers. Now, we, in our investigation, will further, we will make use of this theorem, which somehow encapsulates more or less all the information and the notation and terminology that we discussed so far. So if we have a square matrix with complex entries, it is true also for a matrix with real entries. then the following conditions are equivalent. So A is invertible if and only if the rank of the matrix A is n, if and only if the range of the matrix A is Rn, if A is with real entries, and Cn if A is with complex entries. If and only if the null space of A consists only of the zeroth vector, if and only if the determinant of the matrix A is non-zero, if and only if zero, the number zero, the scalar zero is not an eigenvalue of A, and if and only if the columns of A are linearly independent. Okay, so this part up to here was sort of recollection of what we need to know from linear algebra in order to continue further. Of course, once we go more into detail, if we need some more terminology, then we will introduce it as we go. And now if we look at the problem that we are going to discuss, we have a matrix with complex or real entries that is a square that has n rows and n columns, and that is invertible. And we would like to find the vector x such that ax is equal to b. In this particular case, as we discussed, if we look at the matrix A and we look at the columns of the matrix A, A1, A2, and so on, AN, and we look at A times X, so A times X then will be the number X1 multiplied by the first column plus the number X2 multiplied by the second column, and so on, plus the number xn multiplied by the last column. And we want this to be equal to b. Now, if we see here from our previous theorem, the determinant of A is different from 0 is equivalent to the statement that A is invertible. We know that A is invertible, therefore the determinant is different from 0. And also we know that A is invertible, and therefore the columns of A are linearly independent. So these columns A1, A2, and so on are linearly independent vectors in Rn. And what we're looking for these numbers x1, x2, and so on, xn, which are exactly the representation of the given vector b to us with respect to the basis a1, a2, and an, which is a basis for the space Cn, or if we talk about a real entry matrix in the space Rn. So given a vector b to us, given the matrix A, we know these columns A1, A2, and AN, and we are interested in finding the representation of B with respect to this basis. It is X is nothing but that numbers that are the coefficients of this representation. Of course, if we know that A is invertible, we can just say, oh, we multiply here by A inverse, and therefore on the left, and therefore A times A inverse will be X, and then we will have A times A inverse times X is X, and therefore we will have that X is equal to A inverse B. However, in practice, this is not the formula that in fact is used, because for large n's, which are problems that are coming from real life, A inverse, the computation of A inverse is very difficult, and this is not what people do for various reasons. Another way, so we cannot use this formula to compute X. Another way people may also look at this problem is that we know from the Cramer's rule that the numbers xi, which are the coordinates of the vector of the unknown vector x, have the representation delta I over delta, where delta is the determinant of the matrix A. Since A is invertible, the determinant of A will be different from 0, so this number here will be well defined. And delta I is a determinant of another matrix. What is this other matrix? This is a matrix which you look at the matrix A, and then with this index I here, we look at the ith column of the matrix A. And we remove that column from the matrix A, and we instead insert the right-hand side, which is the vector B. This way we get a new matrix. We compute the determinant of this new matrix, which will be the number delta I. And then we have a formula that the ith coordinate of the unknown vector is just the ratio of these two numbers. Again, for big N and in computation, this rule is not used for various reasons, and this rule has only a theoretical use. So in practice, in engineering applications, people are using various numerical algorithms to solve the linear system, especially for large values of n, for large dimensions. And somehow we can divide all these algorithms for numerically solving the linear system into two big groups. We can say that there are some algorithms that are universal, in the sense that we have the algorithm, and this algorithm can be applied for solving any system. AX is of the form AX is equal to B for any invertible matrix A. And so we have this recipe or this rule for any A. And if our matrix that we have in our hands has more special structure, then this rule basically gets a little bit simpler, which we're going to see here as we go along with the lecture. Or there are some methods that only work for particular matrices. For example, there are methods that are tailored to the particular structure of the matrix A. There are methods that can be used only for cases when A is symmetric or positive definite. Or there are methods that can be used for matrices that are sparse. Sparse means that these are matrices with huge dimensions, but they in some sense are simple because they have a lot of entries that are zeros. Also, if we look at the numerical methods for solving linear system, they can be classified as direct or iterative methods. These are the other two main groups. What are direct methods? These are methods that in theory give you the exact solution to the system after finite number of steps. So you have some formulas and after you perform a finite number of computational steps, then at the end, you will end up with the exact solution to your problem. However, since these methods will be implemented on a computer, every time when a computation is made, namely addition, subtraction, division, or multiplication, the computer is not going to perform the operation exactly. The computer will not use the real number that one has at hand or is the result of the corresponding computation. It will round off or it will approximate this number to a certain fixed net of numbers with which the computer operates, and therefore every time a computation is performed, there will be an error, which is called a round-off error. And it is important to keep track of this round-off errors, and it is important to see, even though the method that is theoretically sound, written on a piece of paper, how this method will be affected by this round-off errors. Another set of or category of methods are so-called iterative methods for solving linear systems. Those methods are methods that do never give you the exact solution of the system. You cannot hope for exact solution anyways, even if you have a direct method, because you have to implement it on a computer, and the computer always will give you a round of error. But in the iterative method, you will perform computations, and after each step, the method will produce some vector that will be an approximation to the exact solution to the system. And the more steps you do of this method, hopefully, if the method is convergent, then you are going to get closer and closer to the exact solution of your system. So those are called iterative methods, and we will discuss both of those methods in our class. And even though in the book they are put in a separate chapters, I will discuss them one after another. So there will be a certain reorganization of the material. Now, we will start with direct methods, and with direct methods, we will talk about forward elimination, backward substitution, and also Gauss elimination. When the matrix A has a special structure, then of course the solution of the system AX is equal to B, or finding the solution of the system AX is equal to B can be easier than if A is a general matrix. For example, if A is a lower triangular matrix, since we want the determinant of A to be different from 0, and the determinant of A, since it is a lower triangular matrix, is a product of the elements on the main diagonal, so we will require that the elements on the main diagonal are different from 0. And so once we write the system AX is equal to B, which is the same as writing LX is equal to B, and now write down that L is a lower triangular matrix, we see that the first equation, which basically is this row multiplied by the vector X, will give me L1, 1x1 is equal to B1. So the first equation will have only one unknown. This is the unknown x1. The second equation will have two unknowns. This is the unknown x1 and x2, and so on. This is the ith equation. The ith equation will have x1, x2, and so on, xi, all these unknowns, and only them. So what is happening then? That's why the method is called forward elimination, because we start from the top, we go down forward and eliminate the unknowns one by one. So from here, since L11 is different from 0, we can write exactly what x1 is. Now, since x1 is known, we use it right after we find it in the second equation, and then the second equation will have only one unknown, and this will be the unknown x2. Then this now will be known. This will go on the right hand side, and then we solve for x2. Once we solve for x2, this will be the expression for x2, and so on. When we get to the ith equation, we will have already computed x1, x2, and so on, xi minus 1, and the only unknown, that effective unknown, we will have by the time we reach the ith equation will be xi, and therefore all the terms here that are to the left of xi are known. We move them on the right hand side, and we find the expression for xi. And finally, when we go to the last mth equation of the system, everything up to that moment will be known, and the only unknown part will be xm. Then we move here this part to the right, and we find an expression for xm. Now we need to count how expensive this forward elimination method is. In your book, they count only the divisions and the multiplications because they require more resources, but in some other books they count the flops. That means they count all the floating point operations, and this is what we are going to do as well. So at step one means that we solve the first equation. We see that we have one division. This is this division. At step 2, we also have one division. This is this division. Step 3, we have one division. But step I, we have one division. Basically, at each step, we have one division. So all the divisions are 1. Then if we look at the subtraction or addition, then here we have 0 subtraction or addition. Here we have 1. Then the next step we will have 2. In this particular, at the ith step, we will have I components. When we move to this side, we will have I components here, and then the operation is done in between each 2 components. So we'll have I minus 1 subtraction.